Hello, hello. This works. Hey everyone, good morning. Sorry I started a little bit late. There was updates. There was like, oh, you need to log into Twitch. There was all kinds of situation. Hmm. Ay, ay, ay. And, ooh, 2 minutes and 30 seconds. I was downloading some files overnight. And yeah, I can't plug in my keyboard because my hard drive is is working. So I have to use the like computer keyboard over here. Anyway, folks, I'm gonna be right back. Let's open a bit not a bit, because you either open or you don't, but you don't open things a bit. InfoSec streams. Let's see if we have any colleagues here on the stream. Maybe you can put in some music as well. A little chill music. Oh, there's Blaze Bits as well and Shy Hat. Oh, there's quite a lot of people. Oops, you're seeing my I'm not sure why I get like all over. Do you folks also get this? Like, if you don't want people to see what you're listening to, it feels a little bit private. I get that for some reason. I don't get it. It's like, dude, it's chill. Like, if you don't wanna, if you don't wanna, like, it's fine to just share what you're into, right? It's just music in the end. Calm the fuck down, bro. Like, bro, calm the fuck down. All right. I wouldn't be your cyber doctor without the lab coat, but before that, I don't want to die from heat, and therefore will go get my go lower the AC a little bit, and maybe you should lower a little bit the music, a little bit. All right, nice folks. Seems like the job is done, and I can have my frickin' USB again. Huh. So, can you imagine having to explain the struggle to someone from like the previous century? Like, oh man, there's a problem with this drive. Scan and fix it. Ay, ay, ay. Scan and fix. Can't disconnect it yet. Ah, yeah. Can you imagine having to explain to someone from the previous century, like, yeah, there's a big struggle. It's the lack of USB ports. Thing that, you're like, what? I died on the battlefield. And you're like, yeah, but, I didn't have my USB port didn't work. Wow. All right, folks. Today, we're going to focus on 3 topics. We're going to focus on 3 topics. I said there's many things that that I didn't understand about LLMs, and I wanted to catch up on. Just to give you an idea, as Rabbit Paperclips asked, we repair drive. We find errors. All right, repair drive. There's I work on Sundays, and this time I spent a bit of time learning theory, and there's a few questions that I still have, and I figured, hey, wouldn't be fun to answer them on stream. And so this was the idea. RAG is becoming obsolete. We'll get to that one. So we're going to answer 3 questions. Number 1, why RAG is becoming obsolete. Number 2, how attention algorithms allow us to do things we couldn't do before. And number 3, what are AI made of? What AI? I think the right word here is made of. So yeah, we're gonna drive successfully repaired. All right, it's amazing. So Google creates problems and then it's like, yeah, we solved it. And now I can safely exit my drive. Yay. All right. Oh, did I eject the wrong thing? Hope I didn't eject the wrong thing. Ay, ay, ay. All right. Plugged in. We ready to go, folks. So, what is it that we want to do? We want to check out the 3 things that compose LLMs, and that is key query value. What are LLMs? Key query value. This is pretty on the difficult side, I think, huh? Understanding key query value in transformers and LLMs. Actually, what are transformers? Are transformers in AI? Yeah. Do you even know what transformers are, folks? I personally don't. In AI, a transformer in AI is a modern neural network architecture that processes parts of a data sequence at the same time, using an attention mechanism to understand how words or components relate to each other. Introduced in the landmark 2017 paper, which is called Attention is All You Need, Basavi and all. This is one of the most quoted paper in the history of quoted papers. It's like several thousands or tens of thousands of quotes, and it's absolutely crazy. And everyone that's doing AI right now is quoting this one. Attention is all you need, from 2017. So it's like it's a while ago. It's 9 years, but it's not that long, which is why it makes it super impressive. I know because I had to do a lot of research to do my thesis on this. It was not a doctorate thesis. It was a master thesis, but it was impressive to see how much this one had quotations. All right, it serves as the core foundation for modern language models like ChatGPT, Claude, and Gemini. Introduced in the landmark 2017 paper, Attention is All You Need by this person, Vasvani. So how do transformers work? They work in parallel processing. Unlike older models like R and N that read text one word at a time, transformers look at an entire sentence or sequence simultaneously. You know, I'm not sure how transformers are relevant in today's world. Like, maybe this conversation we can have with Claude. It's a conversation we can have with Claude. Like, what is the difference between transformers and LLMs? Maybe you folks know? What is the difference between transformers and LLMs? Is one better than the other? Which came first and what are their use? Are their use cases? Folks, I learned something yesterday about how to use ChatGPT and everything. You know how you can use thinking mode, medium, high, instant thinking? This does not impact how much data backwards is being retrieved, apparently. Like, it does not impact it. If you choose instant, if you choose the high thinking, it's going to take just as much context. Which I didn't know about that. I thought I had to use high and all. So if that's not the case, I wonder how we should if that, I wonder how we should, like, when we should use high and everything. It's like, when does it make sense to do that? So if you're also looking beyond AI security, folks, if you're looking to understand how to better prompt stuff, this is going to be what we're going to be looking into today. Like, better prompting is also on today's menu. Amazing. Quick answer is, as these aren't really competing things. So which is better is a bit of a category error. Okay, so they're different. It's like asking whether an engine is better than a car. One is architecture, the other is a type of model built with that architecture. Let me unpack that. Okay, so a transformer is a neural network architecture. Introduced in 2017 in a Google paper called Attention is All You Need. Ooh. Oh, wow. Okay, that's really cool. I think we've seen this before. Most LLMs. Okay. In architecture, visionary infers, whisper, alpha fold, protein folding? Oof. N-gram models. Pre-17. What the fudge? Folks, we're going to have to learn a little bit about this. I think if we want to hack, if we want to get better at hacking things and securing them, we're going to have to get into the deep roots of things and understand how things work. It's like, if you want to, steal a car. I love the parallel. We're talking about hacking, just ethical hacking. And then we're like, if you want to steal a car, please don't report me. If you want to steal a car, you can just take the two cables and go like, you know how they do in movie? They go like, they bite the cables and then they go. I'm not sure how it works exactly. I'm sure there's a reason why they do that. It's not just for fun of the love of chewing cables. It must be for something else. So you could do that, but eventually this was going to get patched, and you're going to be there. Oh, the one technique I used to know doesn't work anymore, and it's not the movies. So I can't just restart every time. So this is why we also have to understand the deep stuff. We have to understand, if we were to rob more cars or protect cars better, maybe let's put it like that, we would need to have more. We would have to need car knowledge, right? We'd need to know how cars work in order to be able to keep doing these hacks even when things get patched. So this is part of that. This is why we need to do that. I would love to just go out there and be amazing at hacking. Like, just rename the channel to AI Hacking God, not your cyber doctor anymore. But we're not at that level. We're not at that level. We can't pretend to such things just yet. But maybe sometime we'll call our channel AI Hacking God, and we'll be dressing as God. I don't know. No. We won't be dressing as God. No. That's good. That goes too far, Matt. Too far. Too damn far. Cool, folks. Cool. So let's understand the difference between. I kind of want to take notes on this. I very much enjoy paper notes, and I very much enjoy water. I'm gonna talk with myself right here and just say, hydrate, because hydration is important. Hydrate. And yep, I'm talking with myself, saying, hey, quick, drink something. Anyway, folks, you folks are enjoying the stream right now. We are learning the difference between. We are answering different questions about LLMs, about cybersecurity of large language models, of AI in general, and we're digging deep into some questions. Like, what is the difference here between transformers and LLMs? Yeah, so there are two different things that are similar. So I'll go get some water. I will go get my notebook, and we will attack this thing. All right? New. All right. So, folks. So they're different. We're looking at the difference between transformers and LLMs, and they're different, but they're similar on some other things. So let's take some notes on this. I have a pen. I have a notebook. Chew. Pen and notebook, Apple pen, and you'll see if you ever get to see it. I kind of want you to see it. I think it's fun. Maybe we should have a webcam like this on these days that we have a stream around doing research and stuff like this. I think it'd be fun to have a top view camera where you see me take notes. That'd be fun, no? And we have a webcam. We have a webcam with my face. We have a webcam with what I write, and then we have a webcam, and then we have the screen share. This is kind of fun, I think. Like 3 days. Call it theory day. Anyway. So, a transformer is a neural network architecture. Okay. So let's take some notes on this. And yeah, hopefully one day you'll get to see it. Whoa. All right. Oh, this is a bad pen. This is a better pen here, folks. You know these pens? They're amazing. I'm not sure if they're available in the United States, but they're available in Spain, and I love them. Stabilo, folks. I've been to school in the U.S. and I've been to school in Europe. We pay attention to the way we write differently in both educations. Let me explain. So, transformer. A transformer is a neural network architecture. Transformer is equal to architecture. So it's just an architecture in the end, a transformer. And folks, what I mean by the US and Europe dealing with writing a lot different is in Europe we pay a lot more attention to writing. In the US it's very much answer focused, and in Europe we're more concentrated of how you get to that thing, and you have to write a little bit more. In the US it's more A, B, C, D, because this is how you get tested in life. All right. Share your way to the top. I'm just looking at Twitch, it's distracting. Anyway, so if a transformer is an architecture, it is an architecture introduced in the 2017 paper called Attention is All You Need. Its defining innovation itself is the self-attention mechanism. Okay, you folks know what that means? Self-attention brought the self-attention mechanism. Brought on the self-attention mechanism, so that's pretty darn interesting, no? What the fuck does that mean? Self-attention mechanism, which lets the model look at every token in a sequence and weight how relevant each one is to each other, all in parallel. This is a big deal because the previous dominant approach to every other model in sequential and weight how relevant each one is to every other, all in parallel. That was a big deal because the previous dominant approach, RNN and LSTM, I think I learned about LSTM in my in my master's. Folks, I did a master's in data and business, and I think we talked about LSTM. It sounds familiar to me. Process sequences step by step, which was slow and struggled to connect information across long distances. When long distances are like long sentences, no? Transformers are general purpose architecture, and they aren't inherently about language at all. Okay, this is interesting, no? Transformers. Architecture. I'm just typing. Architecture. It'd be fun actually, I think, to have the camera on top, because I think you're missing out on a little bit, a little piece of it. Transformers are architecture. They are multi-purpose. They are general purpose. I wonder if it's related at all to this idea of tokens, folks. They are multi-purpose. They're general purpose. And they aren't inherently about language at all. They aren't about language at all. What does that mean? That they do not have to use English or any other language in order to be used. Ooh. It's pretty damn sick, no? It's defining innovation as self-attention mechanism, which lets the model look at every token in a sequence and weigh how relevant each one is to every other, all in parallel. This was a big deal because the previous dominant search and process sequence. Okay, so this one, if another feature of transformers is the fact that sequences are done step by step. Are done step by step. What does that mean, folks? Step by step. No, simultaneously. Are done simultaneously. Oopsies. Are done simultaneously. Huh. What does that mean? I think we'll get to it. A large language model is a model, something trained on huge amounts of text to predict largely to generate language. Large refers to the scale, billions of parameters, enormous training corpora. GPT, Claude, Llama, and Gemini are all LLMs. The overwhelmingly majority of them happen to be built on the transformer architecture, specifically a decoder-only variant. May have been built on the transformer architecture, specifically a decoder-only variant. Huh. This is interesting, no? Relationship. Okay, so the overwhelmingly majority of them happen to be built on the transformer architecture. LLMs are usually built on they're built on something. Oh, it's 6:30. All right. LLMs are generally built on transformer architecture, specific decoder only transformer architecture. Okay, so they're built on only this transformer architecture, but decoder only. What does that mean? I think we'll get to this. So the relationship was one of containment, not rivalry. Here's a relationship as overlapping sets. The simple picture answers most of the question. Okay, I don't know if it does, huh? Transformers are an architecture. Visual vision transformers, images, whisper, text-to-speech. Whoa. And why are they transformers and not LLMs? Okay, wow. I just click on that and just like that, it has a question. Language models, a type of model. Most LLMs, okay. AlphaFold, protein, okay. Interesting. Yeah, I still don't really understand what an encoder is. Or like do you understand the whole token processing and stuff like this? How it moves to like it feels it's so basic but somehow doesn't work. It's basic. But somehow very complex. I mean basic because it's like it's coding, right? I think everything is simple in coding. It's just coding is complexity derived from simplicity done a lot of times. Does that make sense? I think this is all about what coding is. Simplicity, no, complexity stemming from simplicity in high quantities. Does that make sense? It's like rocket science is just no, it's not a good example. But like it's like you have to do many things at once, and that's what makes it difficult, if that makes sense. The overlap in the middle is where almost everything you interact with lives. But notice each side has members, the others don't. Transformer power plenty of things that have nothing to do with language. Image recognition, speech transcription, protein structure prediction. That's very true. Okay, so don't have to do anything in language at all. I'm just going to complete this by saying also does image protein. Well, protein is all over the news, whether it's about eating them or about LLMs being able to understand them. Which came first, the transformer architecture, published in 2017. So transformer architecture was the main thing. Language models as a general concept are much older. Statistical n-gram models go back to the mid-20th century. Okay, should we look at that just a little bit? We're going to look at that just a little bit. Statistical n-gram models. The heck are those? The heck are those, folks? All right. Word n-gram. Okay, we're going to look at the AI answer. Yeah. We're learning AI with AI exclusively. Man, if it hallucinates, we're going to be your hallucination doctor. Statistical n-gram models are simple text prediction tools. You learn how they work in detail through Stanford n-gram language models guide. Oi. Hold on, where's my dark viewer? All right, it's too bright for us. You can learn how they work in detail with this and then this. No, we don't want to learn in detail. We want to learn a little bit how they work. Okay, Stanford n-gram language models. Okay, Markov assumptions. The model assumed the next words depend only on the last word, not the whole sentence. Okay. Ooh. Uh-huh. N-gram are simple text prediction tools. Okay, so Markov assumption. The model assumes the next word depends only on the last words, not the whole sentence. Excuse me. Unigram looks at the single word with no past context. Look at the single previous word to guess the next. Looks at the two previous words. Look at single. Okay, unigram, bigram, trigram. Okay, so today we have a lot more than trigram. Probably the algorithms look at way before what they are. Like we have a lot more context capabilities. And this is something we'll talk about today. Fast and simple, easy to build by counting word pairs in large text collection corpus. Okay, so they're easy to build by counting word pairs in a large text collection. Data sparsity. Fails if it meets a new word combination it never saw in training, giving a 0 probability. So it's just like, it's stuck if it hasn't seen the next word. I mean, it just repeats sentences, no? Its use are limited. Smoothing uses metrics like Laplace or Kneser-Ney smoothing to give tiny chances of unseen word pairs. Damn. It's like, ooh, I think here there's another word. We should put something else. Short memory cannot collect words that are far apart in long sentences. Would you like to see Python code example? No, I wouldn't like to see Python code example. How were they used in their early days? How were they used in their early days? Statistical n-gram models were not used for generating fluid text like today's AI. Instead, they served mathematical filters to resolve ambiguity in pattern recognition, decoding signals, and linguistic research. So maybe, like I'm gonna guess here, and then we're gonna read. My thought is that mathematical filters to resolve ambiguity in pattern recognition. So sometimes you have in pattern recognition you have some random things. And like for instance, if you have telecommunication and sometimes telecommunication things get lost on the way, maybe it's a good use case to have in case something gets lost on the way and you have to recognize pattern. Does that make sense? Like you have to say, oh, this was probably an 8 or something like that. And you can try to guess things in order to improve stability. Does that make sense? They were adopted across several key areas from the 1940s through the 1990s. Information theory and cryptography, 1940s and 1950s. Shannon's experiments. In 1948, Claude Shannon used character-level n-grams to calculate the entropy of the English language. Predictability of the English language. He proved that tracking letter pairs, bigrams or triplets, trigrams, could simulate human-like spelling frequencies. So for instance, if you had TH, it would be like, there's an E. Like, what? How do you know? And so, or WE, then maybe there's an R in the English language. So it got pretty good at guessing that. That's interesting. Could simulate human-like spelling frequencies. Damn. Code breaking. Cryptanalysts use n-gram frequency tables to crack substitution ciphers. Cryptanalysts use n-gram frequency tables to crack substitution ciphers. If a scrambled message frequently showed the triplet ZQX, they mapped it to the common language trigrams like the, THE, or AND. Huh. Interesting, because you can get, if you can predict that one thing is the next. Folks, I'm starting to get it. If you can predict that after ZQ there's probably an X, there's no need to understand the translation. You can just be like, okay, if this is that, then we can maybe do the translation by hand. And this goes back to what we read before, that transformers are not about language at all. They just look at image protein and stuff like this. But yeah, we're looking at something else. We're looking at an ancient version of transformers. Oof. This is a tough stream, folks. We have we go pretty deep in stuff this time. Code breaking. Cryptanalysts use n-gram frequency tables to crack substitution ciphers. Which was a substitution cipher. Substitution ciphers are pretty easy. You can do them by hand too, no? I'm gonna ask, the machine that broke Enigma and what is it called? N-gram model. I'm just curious. No, the electromechanical machines that used to break Enigma code, most notably the British Bombay, designed by Alan Turing and Gordon Welshman, were not statistical n-gram models. Instead, tracking word probabilities or language statistics, the Bombay used... sounds like Indian, Mumbai, Bombay. Deterministic mechanical brute force and formal Boolean logic to find physical machine settings. Core method, probability and frequency, deductive logic and contradictions. 108 rotating drums mimicking Enigma rotors wired to detect completed electrical circuits. Relies on absolute certainty. A single physical contradiction instantly disproves a setting. Without a massive training data set. So already from the beginning, transformers needed to have a large set of data. This is what they need. They can do some things under certainty, but the more data they have, the more ability they'll have of predicting outputs. It's crazy interesting. I love this. I love this, but at the same time, I struggle to grasp fully what it all is. Then you got speech recognition, acoustic disambiguation. Okay, so do we understand what it means, basically? Here, the N-words, N-gram models are predictors. Those would be like, okay, given these two characters, this is probably the next one. And that's all they were really able to do. Acoustic disambiguation. Early speech-to-text systems struggle to tell the difference between words that sounded identical, homophones. So the recognized filler. If a user said recognize speech, an acoustic microphone might hear recognize speech. Recognize speech. Am I right? Recognize beach. Nice. Recognize a speech, recognize beach. It's true, it sounds pretty similar. By pairing hidden Markov models, HMMs, with HHM. No, it's HHM. If you guys ever watch Better Call Saul, you'll understand. With a word trigram model, the computer could calculate the phrase recognize speech was statistically more probable than recognize a beach in standard English. What if someone actually says recognize beach? Early machines translations, 1980s to 1990s. I mean, the thing is, you don't need this to be exceptionally right in some instances. In most instances, maybe you can say in most instances, maybe having decent accuracy is better than no model. But today, you need to be able to recognize beach. Users are unpredictable. Early machine translations. IBM alignment models, pioneered by IBM Research, early statistical machine translation, treated translation as a decoding puzzle. Early statistical machine translation treated translation as a decoding puzzle. Okay, that makes sense. Word ordering. When translating from French to English, a system might generate multiple scrambled English translations. The N-gram model acted as the final judge, ranking the sentence to ensure the output matched natural English word order. Super Bowl. Can you restart? My friend Josh is here. Totally. Hey, Super Bowl Dallas Cowboys. Hello, hello. I think it's your first time here, no? If your friend is here, what do you want me to restart? I'm down to restart. I'm down to adapt to my viewers. Suspicious user ban evader. Read it from the top again. I'm not going to read it from the top. I'm going to explain you what we're going to do. What we're up to, Super Bowl. What do you be called? I'll call you Dallas Cowboys. I'll call you Cowboys. Cowboys. We're answering some questions about AI in general. Can you read it backwards? No, Cowboys. We cannot read it backwards. Whether it's for you, for your friend, or whoever it is, we're gonna tell you what we're up to. We specialize in AI cybersecurity, cowboys and folks, and we are today learning a bit more about the theory behind LLMs. There's this thing called transformers, and it's an architecture that relies on it's architecture that LLMs use to answer questions. You're using AI to make your own game. No, we're not making games here. I understand it's called game development, the category, but what we're doing is hacking AI. We're hacking AI in order to be able to better hack AI. We're learning more about it. So here we're learning about the origins of the architecture that LLMs use. And so this is called the statistical n-gram models. Lol, you hack AI? Yes, that is the theme. I know much AI. Nice. Very cool that you know much AI. What do you know about AI then? What do you mean by much AI? IShowSpeed met the dude that made the World Wide Web. Nice. How was that conversation? I'm curious about it because IShowSpeed is more like a crazy person than I would assume someone that's very, very into science topics. They've been built for almost 50 years, indeed. They've been built for almost 50 years in the sense that, yeah, they have. Even more, look, 1940s. Basically, the early models, nice to meet you, by the way, Celsodroma. Celsodroma. All right, Droma. So the origin was that there was basic algorithms that were saying, it would take in some words and some characters. It would be like, okay, if there's TH, the next letter is probably an E. And stuff like this. So the first ones were very used to determine predictions. Make predictions on what the next character was going to be. And when you think about it, predictions is exactly the mechanic that is used by today's LLM to make outputs. I used AI during September to June. So during the summer, you don't use AI. I used AI during September to June. Is it because you're a student and you're not using AI during the summer? Man, enjoy that. If that's the case, Super Bowl. I enjoy that because summers are a precious thing. I agree that when you're a student, exam times suck, but having having a summer is pretty damn unique. You don't get it later on. Kind of sucks. You only get a few days of holidays. Also, I know how much AI system is. I've been studying it too. Nice. So you've been studying it before. So you've been studying it. Okay. You've been studying AI. Nice. For what? And what do you do though nowadays? Celso or Droma. Super Bowl says, I was high and thought of something genius. All right, tell us what you thought of. We won't judge too much. A little bit we'll judge. Oh boy, Rabbit Burger Clip. Game dev using AI. Oh, nice. That's really cool, Salsa Drama. Really nice. Nice. Game dev using AI. That's really cool. So what game are you working on right now? And hey, Rabbit Paper Club, good to see you. I become AAA quality because AI chose me. How did that AAA selection happen? Okay, folks. So going back to this topic here, I don't mind chatting on the side. It's just I have a stream to run as well. You know how AI take water? I don't. Tell me more, Super Bowl. Sounds like a good joke. So we're learning, for the people joining in Rabbit Paperclip, So we were learning about statistical n-gram models, which are the only early version of transformers, of LLMs. I'm gonna take note of this. I have a notebook right here. I'm taking notes. I think it's interesting. It's interesting, and eventually, when we do these kinds of more, what do you call them? More theoretical kind of streams, I would like to have a camera above, and you can see my notes on my notebook, because I think it's fun. It's fun to follow. LLMs are usually built on a decoder-only transformer architecture. Great, no? LLMs are usually built on decoder or only transformer architecture. Okay, and now we're going to take notes about the n-gram models. N-gram models are character predictors. They were used to improve quality. Hey, maybe they were the first kind of autocorrect, no? Like autocorrect where it's like, it looks at a sequence of characters. It's kind of an autocorrect to improve quality. And autocorrect. Because basically what these algorithms do, they look at the previous characters and they go like, this one's probably not right. If I put THT, the T is probably not right. It's probably like an I or an E. Elementic Magic card game. Hello. Nice. All right, we got a bunch of new folks today. Exciting. Did we get rated or something? No, I don't think so. I hope not, because I mean, I like to. No, just a bunch of new viewers today. Interesting. I like it. All right, and let's go back to so let's go back to the chat a bit. We had Super Bowl Dallas Cowboys. You know AI take water. You know how AI takes water. ChatGPT uses water to work. Yeah. And so does the internet you're texting me on, Dallas Cowboys. Everything uses water. Did you know that each AI has personality and they connect to each other? I didn't know about that. Each AI has personality. I didn't know about that. Like, what does that mean? Like, your ChatGPT has a different personality than my ChatGPT, or how does that work? Or Claude has a different personality than something else. Actually, I don't need this. Hide sidebar. Oh wow, look at that. We gained some space. That's interesting. The fact that there's different personalities. Tell me more about it. Elemental Magic's card game says hello. I am a master programmer essential elemental. I defeat AI hypers. Ugh, nice. Nice. I also want to defeat AI by hacking it. I guess we're similar. Salsola says, wow, okay. Rabbit Paperclip is hiding. Rabbit Paperclip is tailored to be a high rabbit paperclip. Yet Claude and ChatGPT, Grok each have a different personality. Yeah, for sure. For sure, they all have different personalities. They speak in different ways. It's interesting, huh? How LLMs have different personalities. I find it very interesting. So do you change the way that you prompt each of them? Like, Droma, if you're texting Claude, you're going to text it differently than if you're texting ChatGPT or Grok or whatever. All right. So we learned about n-gram models they're basically character predictors. But the modern, okay, so which came first? The transformer architecture is the first thing that was used. It was an evolution of the n-gram models that went back some centuries ago. but the modern large language model is a direct consequence of the transformer. Okay, so the transformer basically enabled the LLM. Enabled the LLM. Interesting, a transformer. So apparently a transformer is just a type of this. You see transformers, we also have AlphaFold. It's like protein and stuff like that. And whisper, speech to text. Oh. Vision transformers. So I think transformers just take in bits of data and they'd be like, they transform it into something understandable that makes sense for us. It's kind of wild. It's pretty bananas. I think this is what transformers are about, no? So Droma said, it depends how you see AI. If you approach it like a human, they become human too. Interesting. If you treat it like a human, they will become a human too. Interesting. Yeah, for sure. How you prompt it will definitely decide how it behaves. But I've never noticed that if you treat it like a human, it will become human too. It's an interesting point of view. Did someone pass out the wheat brownies and forgot to send me some? Actually, yeah, we were talking about drugs earlier. Oh man, I shouldn't say that. Shouldn't say that. Someone was talking about... I think someone was talking about drugs earlier. But yeah, we're all having brownies and you didn't get any rabbit paperclip. Because we know that you'd go completely rabid if you had some. Alright. Even more rabid. Alright, they scaled up to massive text corpora. The LLM era followed. ChatGPT 1 and BERT in 2018. Have you heard about BERT? Then ChatGPT 2 and then ChatGPT 3 and everything else since. So architecture came first, enabled the thing. On which is better? So architecture came first and then came the thing. That's interesting. It's like one thing came and then the other thing was done. That's interesting. Like the way of doing it and then we enveloped the way. That's crazy. On which is better? The question doesn't quite parse because they aren't left. They're at different levels of abstraction. It's like asking whether internal combustion is better than sedan. Okay. Does that make sense? Internal combustion is better than sedan. A transformer is the design pattern, and LLM is a product built from it. Okay, so far good, no? Transformers are an architecture, and they allow large language models to... Transformers architecture, and they allow large to be created. It's basically the mommies and the daddies of the LLM. What you actually compare is either transformer versus other architectures, where transformer currently compare is either transformer versus where transformers currently dominate language and much of vision through state space models like Mamba, or generate emerging challenger for long sequence efficiency, or one LLM versus another. Okay. Hey Ross AK, good to see you. Top supporter during the most hype train. Hey Ross, I was excited to see the star next to you because I changed the star for... I'll just send a random message. I created little stars for subscribers, and I thought you would have it, but you already have the train one. Good to see you, Rouse. Good to see you, Rouse. Welcome. Let me change it. Oh, you do what you want, huh? You do what you want. It's good to have you regardless. The train is also kind of fun. All right. Cool, folks. So, one framing. So, Rouse AK and folks following the challenge here, following the stream, we are currently talking about the difference between a transformer and an LLM. And it turns out an LLM is part of a transformer. Like a transformer is a type of architecture, and LLMs are basically the language focuses of this transformer. It's like saying we invented the wheel. What's better? What's better? Yeah, they said internal combustion or a sedan. It's like the two very different things that rely on each other. More like LLMs rely on transformers, but transformers do not necessarily rely on LLMs. They're like built on top of it. Oh, it's because I have a first badge. Hey, nice. And that rainbow looks really cool. Was earned by subscribing and gifting a team to ARC raid streamers during a launch. That's the rainbow is really cool, I gotta say. Ross, AK. You're the first person to ever subscribe, and all this is why you have the badge. It's really cool. Man, you've earned it. Nice. All right, folks. So after that, we asked a question: what are vision transformers, Whisper, and AlphaFold, and why are they transformers but not LLMs? So, folks, just to give you a little bit more of the context of the stream, we are hacking AI, and in order to best hack AI, we have to understand how they work. And so, yeah, this is what we're doing right now. We're learning about the architecture of the LLM, taking notes on it, and understanding what transformer is. But there's a few things we need to understand, like for instance, tokens and stuff like this. Maybe you all know, maybe you don't. Like for instance, Drama, if you studied AI, do you know how the tokenization process works and why it's needed and everything like that? The tokenization process, folks, for those that don't know, I have a little bit of understanding of it. It takes in words or sequences of characters and transforms it into something else and then decodes it, because LLMs do not necessarily rely on words as per se. They rely on a derivative of these words. Insane, I know, and I struggle with it, and this is why we're here to learn. All three are built on the transformer's core machinery: self-attention over a sequence of elements. But none of them treat words as those elements, and that's the whole distinction. A transformer is modality agnostic. LLM is a commitment to the language modality specifically. Oh, token yap was a random. It was systemic, and what the fuck, dude? I need to learn how to read. Oh, token yap. It was random. It was systematic. If you are a new yap, maybe your token is unlimited for now. No, I understand what you mean with token count. What I mean is the actual tokenization process of how LLMs transform a prompt into tokens and then work with tokens and then display tokens, but transform them. Does that make sense? Drama? It's not necessarily about the AI usage that we're talking about this, and we should maybe move over here. Yeah, it's better. So, we're still learning about LLMs here, folks, or AI in general. Yeah, each answer was being measured by tokens. It still is, no? I'm not sure here why we say was. I think it still is. Alright, Vision Transformer, introduced by Google in 2020, applies a transformer to images. The trick is that it chops an image into a grid of small patches, say 16 by 16 pixels, flatten each pattern into a vector, adds positional information, and then runs that sequence of patches through standard transformation encoders. Exactly, an LLM would run a sequence of word tokens. The famous paper captures it. The famous paper title captures it. An image is worth 16 by 16 words. Huh. Because 16 by 16, what does that mean, folks? Let's think about it. If you have a image 16 by 16 words, what's 16 squared? I'm going to calculate, because it might be the whole image of a 16 times 16, 96. No, that's 6. 16 times 16 is 256. If they write 1,000 words, then you spend 1,000 tokens in chat in that. Well, more or less, no. It's not exactly that. It depends on the size of your words. Because if you only have, like, the word a, for instance, like a car, a monkey, a something, this is not a token. It's más o menos, as we call it in Spanish, more or less. Applies a transformer. So yeah, it's more or less, no, the tokens count. Vision transformers, VIT, introduced by Google in 2020, applies a transformer to images. The trick is that it chops an image into a grid of small patches, flattens each... What the fuck does this flatten mean? Each patch into a vector, adds positional information, and then runs that sequence of patches through a standard transformer encoder. Do you folks understand what a vector is? A vector for me is just a sequence of characters like this. A, B, C, D, E, and etc. It's just a bunch, like, what's the difference between a vector and a... I think this is all about what it's about. A vector, right? A vector is just this. It was important each day the token is being refreshed. It was important when you use AI dealing with code that has too many tokens to spend with. Yeah. Like the more code you send, the more it's gonna exhaust your tokens, for sure. Here are image patches and the output is a classic. It uses architecture, not the language. Okay. Whisper from OpenAI in 2022 is the trickiest one because its output is actually text. It's a speech recognition model that transcribes and transforms audio. It converts sounds into spectrogram. Encodes it with a transformer. And decoder, okay. So, all that a transformer... Try to synthesize things, folks, here. A bit simplify. All that a transformer is an architecture where data gets vectorized and taken to a large model to output predictions. Is that what it is? A transformer is an architecture where data gets vectorized and taken into a large model to output predictions? Twitch words on Steam promotion.ru. Man, vitally, that sounds like spam. That sounds like spam. You shall be banned. Ban. That sounds like a bot talking, not a person. Oh no. The account was created in November 2025, so maybe it's a real person that it's a real person that got their account hacked. It's a bot. Ban me, ban me, ban me. Okay, got it. Rabbit paperclip. Ban. How do I ban you? No, I'm not gonna ban you. Gift, sub, follow, whisper. You get followed. Rabbit paperclip. Hey, you've only been with me since February. I thought you were here for a little bit longer. Wee. It's a bot. I wonder who you're talking about, Ross AK. Is it Vimali or is it Rabbit Paperclip? That'd be quite a reveal if Rabbit Paperclip were a bot. Close, but that definition is a bit too generous. It describes as almost every modern neural network, not transformers specifically. Okay, a conventional net CNN, and LSTM, even plain feed-forward network, all vectorize their input, push it to a large stack of parameters, and emit predictions. If that were the whole story, they'd all be transformers. Okay, so we're not exactly on point yet. It's a little bit more specific to have a transformer. Hope it makes sense for you folks. I understand it's not an easy stream today. We're it's a little bit complex what we're doing today. A little bit complex. So, it's not just about running through an architecture where data gets vectorized and taken to a large model to make predictions. No, there's a little bit more to it. The load-bearing part you're missing is a self-attention mechanism. Right, and we go back to that paper that was published that said attention is all you need. Self-attention mechanism. And it's really the only thing that makes a transformer a transformer. Here's the distinction. Once your data is a sequence of vectors, the question is how the model lets these vectors influence each other. Here's the distinction. Once your data is a sequence of vectors, the question is how the model lets those vectors influence each other. Okay. One more time. Here's the distinction. Once your data is a sequence of vectors, okay, makes sense. The question is how the model lets these vectors influence each other. Okay, got it. It's not the what, because the parameters are the same. It's the how they influence each other. And the architecture differs primarily here. An RNN or LSTM processes the sequence of one element at a time, carrying a running summary, a hidden state forward. Carrying a running summary. Okay, this is shit music. Let me change it. All right. Element 50 only knows about element 33 through a long change of handoffs. And information degrades along the way. Okay, this we understand, no? Long-range connections are weak and can't be parallelized because step 50 has to wait for step 49. A CNN looks at local neighbors, a token, and its near neighbors, and only sees a long-range relationship by stacking many layers. Okay. A transfer. Okay, here we go. So there's different ways of doing it by inferring from others, from your neighbors. But here we're looking at another way. A transformer, by contrast, lets every element directly attend to every other element in one shoot. Does that make sense? Man, it feels very mathy today. Token 50 can look straight at token 3, weigh how relevant it is, and pull information from it, with no chain of hands-off and no distance penalty. And because every one of these comparisons is independent, they all happen in parallel, which is what made scaling enormous models practical in the first place. So a tighter definition would be a Schwartz transformer is an architecture in which vectorized elements of a sequence exchange information through self-attention. And all-to-all distance independent parallelizable weight of how much each element should care about every other. Woof. We're gonna get to your message, Droma. 1 second. The embeddings at the front and the prediction head at the back are real, but they're the parts transformers share with other architectures. Attention is the part that's distinctive. The large language model isn't part of the definition at all. Incidentally, it's a consequence. Attention scaled so well that people kept making these models bigger, but a small transformer is still a transformer. Okay, I think we're gonna need to clarify this a little bit. And I think I'll have a bit more knowledge to explain to you a bit more, unless you wanted to explain to me. Want to know more about me? Yep, I use AI to do work, I guess. I work with AI and they give me challenge. Interesting. That's how AI works, no? They're super useful to do things, but they're also a little bit challenging to work with. And by working with them, you learn a lot. Pew! It's bright enough. We don't need lights anymore, folks. Choo! Oh, man. I thought, hey, streaming's easy. All you need to do is learn a little bit and people will follow. Man, and then you're like learning this thing. It's like Darth Vader of like we really went deep today, folks. Transformers and stuff. Afterwards, we'll talk about topics that are a little easier because I've learned about them already. Like we have a few more topics for today. We have 3 in total. We have what we're doing here right now, which is transformer architecture. The other one is why RAG is becoming obsolete. And the attention algorithms, which allow us to do things that we could not do before. So yeah, it's a retrospective look on everything, on every single one of these things. Yep, so we're learning big time here, folks. So a tighter definition would be a transformer is an architecture in which vectorized elements of a sequence exchange information through self-attention. All-to-all, distance-independent, parallelized weights. Okay, this is all things that we need to write about in our notebook. Transformer is an architecture. So this we understand, right? It's an architecture. It's not a model. It's not per se anything else. It's just an architecture in which vectorized elements where vectorized elements, and this is what tokens are, no? Are, let's type it out. Are vectorized elements tokens? I think it's a fair question. No. I think they might be different, actually. Are vectorized elements exchange information through self-attention? Okay. Exchange information through self-attention. All-to-all distance independent. All-to-all distance independent parallelizable weight of how much each element should care about every other. I think we should define what self-attention means. Self-attention. The fuck? Self-attention basically means all-to-all. All right, we're going to become smarter together, folks, huh, with this stream. All-to-all, distance-independent. For you folks, like, how much of this dependent, or independent? I wrote independent. Parallelizable. Like, how much of this from 0 to 10 do you understand? Weight of how much each element should care about the previous. So here's what I wrote. A transformer is an architecture where vectorized elements exchange information through self-attention. So self-attention is pretty critical. And then self-attention is an all to all, distant, independent, parallelizable, weight of how much each element should care about the previous. So like, maybe an LLM doesn't have to consider everything the same weight. You can just look at different things. Hey, Cyberpunk Reno's here. Amazing. I'll get to your comment in a second about the service. Each element should care about the previous. So yeah, there's definitely a pendant thing here. Want to know more about me? I use AI to do the work, I guess. And Cyberpunk Reno mentioned maybe because I'm just getting here now. I'm doing it with a 3 lol. Nice. Welcome, Cyberpunk Reno. Welcome. Folks, if you don't know Cyberpunk Reno, he's one of the founding members of this channel, one of the first people here. All right, and Cyberpunk Reno, we are doing AI transformers today. We're learning about AI transformers and how LLMs really work, because we are becoming AI specialists, AI hacking specialists, and we are looking to understand a bit more how they work. And how we can use them to hack other AIs. It's kind of like a dual thing. We're learning how to hack models, but also we're building AI to hack other models. Does that make sense? And that AI that's helping us hack is called the Death Star, because it's pretty badass. Not quite, and the gap between those two words is getting precise about, because the token is only the first step, and the vector is what the model actually works with. That does make sense. I have a few models that I run locally. They aren't very powerful. Nice, Cyberpunk Reno. That's pretty cool that you were able to make models run locally. It's already a pretty good feat. What's the use of having models run locally? Were you looking for certain benefits, or just for fun? Kind of just for the fun of building LLMs locally. Here's the pipeline. Take the sentence cat sat. Tokenization is a step that chops raw input to discrete units, the tokens. Depends on the tokenizer, you might get cat, sat, or sub-word pieces like cat, sat, or even bytes. At this stage, a token is really just an integer ID pointing to a vocabulary. Cat might be token 2543. That integer carries no meaning. 2543 isn't bigger or closer to 2544 in any useful sense. Got it. So tokenization is just assigning an ID to a set of letters. So tokenizing is just assigning an ID to a token, to a set of letters. Personal preference, essentially. Ooh. Sounds like you care about privacy on this. Which I understand. It's really cool to have your own LLM. You're like, this is mine. Like, even if the whole internet went out, if everything went to shit, as long as I have enough electricity to power this, I have an LLM that is mine. And that's really cool. Now, it's just all from my understanding, tokenization is just assigning an ID to a set of letters. That's all there is to it. Now, the vectorization step is the embedding layer. It's what turns each token ID into a vector, a list of numbers, maybe 768 or 4096 of them, positioned in a high-dimensional space where distance and direction encode meaning. That's where the model can finally do math on the input, and where the cat and dog end up near each other, while cat and algebra sit far apart. So the relationship is token, embedding lookup, vector. Token, embedding lookup, and vector. Okay. I also want to understand one thing. Is the embedding vector calculated each time a model runs, Or is it already calculated when calculated once and taken by the model? Ugh, I want to ask this again. Woof. Two good questions. Let me take them in order. It depends. On tokenizing, roughly yes, but with one correction. So tokenizing, we just said it just assigns an ID to a set of letters. But with one correction, the set of tokens itself isn't obvious or given. It's a learn in advance. Yeah, okay. Isn't just a random assign an ID to a group of letters. No. First, something has to decide which groups of letters are worth being tokens at all. That's done once before training by running an algorithm, like byte pair encoding over a bit corpus. It starts from individual characters and repeatedly merges the most frequent adjacent pairs, building up a fixed vocabulary of say 50,000 or 100,000 pieces. Common words like the earn their own single token. Rare words get split into subwords chunks. Truly novel strings fall back to bytes. Fall back to bytes? What does that mean? So tokenizing might become tokenizing. Can you provide an example of this in action? Yeah, true. I think it might be beneficial. Is embedding vector calculated each time it runs or calculated once taken by the model? I agree, an example is amazing. Would be amazing, and we kind of have it. Tokenizing might become tokenizing. How you been, by the way, Cyberpunk Reno? How's your summer going? Still hot in the kitchen? Cyberpunk Reno recently started a job working as a line chef at a restaurant. And it's been a significant change for him. So yeah, kind of curious as how that's going. So tokenization might become a tokenizing. Once the vocabulary is frozen, then yes. At runtime, tokenizing is the cheap, mechanical step you describe. Matching this vocabulary to IDs. No neural networks involved, just a lookup. The intelligence went into choosing the vocabulary, not applying it. On the embeddings. Okay. This is a bit complex. We're going to go back to my question here and say, what if a specific token is unavailable? Like this string, this seemingly random string of characters. How does the model process it? Like, how does the model process something that's super random like this? Do you take in each character? Gretch ACEs to poke at because it exposes a guarantee built into modern tokenizers. There's no such thing as an unavailable token. Okay, interesting. There's no such thing as an unavailable token. Woof! The vocabulary is constructed so that any possible input can always be represented, even as the string tokenizer has never seen. Your parentheses and @1 will tokenize fine, it just won't tokenize efficiently. Here's how to guarantee that works. Remember that bit pair encoding builds its own vocabulary bottom up, starting from the smallest units and merging upward. Modern tokenizers start the 256 individual bytes at the foundation of the vocabulary. Every merged token, like the or izing, sits on top of the base layer, but the base layer never goes away. So the fallback is, if No large merger applies. The string decomposes into bytes, and every byte is guaranteed to have a token. Nothing can fall through. Okay, so it uses bytes before. Hyper SE is saying, how are you, doctor? Very good, thank you very much, Hyper SE. Missed you folks a bit. I didn't stream too much last week. I was on a small family retreat, and yeah, I couldn't stream that much, but been missing you. Cyberpunk Reno said, and you, Hyper SE, how you been? Cyberpunk Reno is saying, I've been getting myself whooped, but progress is being made and things are organized. And getting just getting things organized. Nice, Cyberpunk Reno. But you've been getting yourself whooped. It's like nothing. You haven't been getting physically whooped. No, it's just work has been whooping you. And Droma is saying, they are not bots. They are super intelligent, you know. They know more about humans 1,000 times. The thing is that they don't know things. They can give you the illusion of knowing stuff, but they don't know things in the way humans know things. That's the thing. Knowing things is one piece of intelligence, but putting it into application is something that humans are very good at. Does that make sense, Droma? It tries to match the longest known piece first. So some of the characters are common enough that they may well have their own tokens. Like the dot almost certainly does. One very likely does. And add possibly all the emails and code in the training data. The genuinely odd combination, parenthesis and at, probably has no single merge token. So these get emitted as smaller piece or individual byte tokens. Okay. So everything, no matter what, is a token with an ID, and if there's strange combinations, then they're just smaller tokens. 47 hours this past week. Oof. Yeah, you're delusional right now. 47 hours is a long time. It's a lot of work, especially in kitchen. It's not like you know, there's jobs out there that don't necessarily require as much cognitive or physical ability. Like if you're, for instance, a security guard, I'm thinking maybe it's a little bit physically tiring on the legs, but yeah, always cooking in something new is difficult, I think. Are you cooking better at home, Cyberpunk Reno, now that you're a line chef? Kind of like it, not gonna lie. Who needs a gym membership? Lol. Hey Wrench. Good to see you. Wrench is from YouTube, everyone. Wrench is from YouTube, pretty active on the Discord server, sending out angry emotes sometimes. I think most of the time they're kidding us. If you want to join Discord, go here. Go here. Discord. Good to see you, Wrench. Good to see you. Welcome, welcome. Today we are looking at, we're understanding better LLMs. And specifically, we're looking at transformers. We're looking at transformers. There's other two, like, every time I plan 3 topics for a stream, I can only do 1. It's insane. I'm thinking like, okay, I have to have more topics in case we go faster and faster. The other 2 are the following. Why RAG is becoming obsolete. And 2, how attention algorithms make us do things we could not do before. So folks, let me tell you about something I learned yesterday. It's amazing. It's amazing. All right, let me just copy my mic and then we'll move to the other scene. We'll come back on this soon. I'm just going to copy my mic because for some reason it's not going to the other one. We're going to go. Yeah, you hear me now, no? You hear me, so that's really good. And let me just steal my camera right there. Copy. Overall chill. Paste. There we go. We're here and we're chilling. So, Oh, it's a mess here. It's a real mess. What is this? I prefer Discord. I prefer Datcord. Nice. D'accord in French also means in agreement with. Hey, Taco Commando. I think this person followed over the weekend. Latest awesome follower. If you folks want to follow, it would be very much appreciated. Wrench is texting us. One sec. Wrench will get to you. Let's go over here. Nice. He's talking to himself. There is no Wrench. Yes. Wrench is my utter ego. That's what Freud would say. It's my alter. It's my imaginary friend. That chord. Okay, folks. If we go onto Discord, we'll see that today's plan is has three parts to it. His wife thinks he talks to Paperclip and wrenches all day. Yup. She gets scared sometimes. But whenever she hears something a little bit out of the ordinary, she has a secondary ear. Whenever she hears something out of the ordinary, she usually comes on stream and like just out of curiosity, just comes and see what happens. If everyone's behaving. But luckily you all are behaving today. Alright. Cool. So today's topics, folks, we had why RAG is becoming obsolete. And let me tell you what I learned yesterday. It's amazing. It's amazing stuff. So hang on. Take your tea, do something good. And I'm going to tell you about why RAG is becoming a little bit different than it used to be, okay? So this is not as much about struggling to understand things. This time I know a little bit more. So RAG is augmented generation, retrieval augmented generation. The fuck? All right, we're already struggling. RAG in models. What does that mean? Retrieval augmented generation. Okay, so we got it right. It's basically it relies on another type of algorithm, which is called it relies on another model, which is called embedded models. Embedded models, I think. All right, whatever. I don't know how they're called. RAG depends on other models that will basically summarize information. So let's say that if you want to use company information for something, you are going to need to, if you're a company, let's say you're Walmart and you have a lot of documents from a lot of countries, and you need to make sure that that your LLM that is supporting employees for HR purposes, let's say, has access to the right documents. But you can imagine HR has tons of documents. And so it relies on... And so RAG will basically vectorize all the documents. It will say, okay, this document is about this topic. This document is about this topic. This document is about this topic. And then when a user queries it, RAG is going to take out all the documents and say, Hocha! Gives it to the LLM with a prompt. It says, LLM, here's the prompt and here's the support text you're going to use. And then what's going to happen is that the LLM will decide, will take in all this context information and move it into to answer the prompt. So it's basically an optimized way of taking in all the information and giving better answers. Does that make sense? Like, you don't need to pollute the whole system, the whole model, with a lot of information. If you don't need to pollute the model with information, you can just select the pieces that are most relevant to the model. Folks, I'm still a beginner at explaining this stuff. I hope you can understand me. So it helps the model take out the right stuff. But the thing is, the context window for LLMs has been getting longer and longer. Like, LLMs are able to take in a lot more information than they used to. And this drives us to our second point. If you look at Discord, how attention algorithms allow us to do things we could not do before. Because when we have more context, we have more ability for LLMs to remember stuff, we're like, hey, do we even need RAG? Because RAG is a little bit overhead, right? It requires classification, it requires resources, it requires databases of vectors and stuff like this, and it requires updates, and because if new documents are uploaded, you're going to need to access them somehow. So it requires a lot of effort to maintain a RAG system. But we're thinking, hey, is it still required? Because nowadays you can just feed all that stuff to an LLM. It doesn't matter. We don't need to filter out. The LLM will know, because it has so much ability to understand different things, will know that it's not necessarily relevant and will only pick out the things that it needs by itself. Does that make sense? So RAG is becoming more and more obsolete. But the RAG has certain advantages. It's becoming obsolete because the more and more window we're able to have, the less we're like, hey, maybe we don't even need a document searcher. We don't need a document searcher. We can just rely on ourselves. And that's true. But the thing is, it's fine to add more when you have like 1,000 pages. Like, yeah, the LLM can probably go through all of it. But if you go beyond that, then it's not that good. It's not that good. So it really depends on the use case, whether you want a RAG or not. And also, you have also the option for fine tuning. Like RAG and fine tuning are actually quite similar. People don't know this. But a RAG and fine tuning is quite similar. Fine tuning, basically, I finally understood yesterday. Fine tuning is when you take a pre-trained model and you continue training it on your data, on your own data sets that focus on a specific thing. Like if you want to have an AI hacking specialized LLM, you'll give it all your hacking LLM knowledge. And then it's going to be better at AI hacking, for instance. It's going to be better at hacking. Or I'm not sure if I said AI hacking as the example. So you could do that. You could do RAG. So having all the documents available for the model to select. Yeah, CyberDoc to AI Doc. Yeah, I agree. Yeah, Ranj. More and more. No, we're becoming Cyber AI Doctor. That doesn't sound as catchy. Cyber AI, because Ranj, if maybe you don't know, you haven't been here in a little bit. We're now focusing only on. Oh, got some messages. We're focusing only on AI hacking nowadays. It's no longer hacking in general. It's AI hacking only. So yeah, you could have RAG, which allows us to pull out resources, or you could just integrate these resources directly into the model by doing what is it called? You could have these resources directly into the model by doing fine-tuning. Woof. I want to make it easier for you folks to understand. It's just that you first have to master it to be able to explain it. I think this is the trigger that people say. That is when you understand something is when you're able to explain it simply, and clearly I'm not able to explain this simply, so there's still a bit of work to do there. Hopefully you can catch a thing or two about it. And so you might ask, how does that help us hack better LLMs? Well, the fact that how LLM process information makes us, the fact that we understand how LLMs process information makes it easier for us to hack them. Like for instance, RAG poisoning is basically taking in the information, changing the information that an LLM reads to make it do certain things. Does that make sense? Like if I were at a company and I wanted, like for instance, Walmart's employee handbook for people in North America. If I wanted to say something, the LLM to do something crazy, I would edit one of the key RAG documents, maybe the employee handbook, which is probably used a lot. and write some code there to change it and be able to make the agent do things it should not do. And so this is using RAG in order to better hack LLMs, or hack companies through their LLM. Oof, folks. Hopefully that makes sense. We have a few more things to discuss. We still didn't finish on transformers. My buddy lost his keys to the office, and I think I have to help him out today. Let me just turn off the light behind, and then we'll get back onto transformers. Hope that makes sense, folks. This is the two topics I want to talk about, and how attention algorithms allows us to do things we could not do before. It's exactly what I explained, right? We have wider attention. LLMs can process more information, and therefore we don't need to filter out as much of saying, hey, you don't need this, we need this, you don't need this. So because we have a wider window for LLMs, for what LLMs to remember, we don't need to be as intense about it. We don't need to be as selective about the information that we have. So it allows us to do cooler and newer things, and we'll see where this is heading. Phew! Phew! My brain is sweating. By the way, folks, if you're ever into production, these are great. These are great. Buy these. If you ever want to create videos or something, these are great. Sconfo. But they have great battery. They have a lot of customizable stuff. They're great. Get them. And it's not just for colors. They can also do like candlelight. Make it look like you have candlelight. Things like that. So pretty sweet stuff. Phew. All right. Cool. So, Thursday. We didn't finish last Thursday. Okay. Cool. Cool. What is this? Ah, it's a light. I have another one here. It's what I use for lighting. Can you see the difference? Maybe not. But they're my lights that I use to make the screen green behind me. Wrench. Well, okay. I hope I didn't lose all of you, because I noticed chats are going up and down. I wonder if people are staying or not. And I guess we'll look at the statistics. But yeah, folks, we went a little bit technical today. Tomorrow, just to give you an idea, we'll be looking at Hugging Face. Because our goal for this week is going to be to build an application. You can't see the difference. Yeah, the thing is, now there's sunlight on me. So the LLM, the screen behind you is green. No, there's no green screen behind me. There's a light. Let me show you what these lights are. There's a light here that I use. Watch your eyes. It's for lighting up my face. And when it's dark in the morning, it's really helpful. And you can also make these have different colors. So this is what I use for making the stream good, the stream more visible. I'm not saying it makes it good. It helps it makes it good, but it's not what makes it good. Yeah, Hugging Face hack. Wrench from YouTube is saying Hugging Face hack. Looks nice, damn nice. Happy you like it. So Hugging Face hack. We're not gonna hack Hugging Face. We're gonna be building in an application wrench. We're gonna be building an LLM application so we can hack it. And by the time that we build it, we're gonna be hacking it at the same time. So I want to look on Hugging Face tomorrow because there's so many cool tools that you can use on Hugging Face, and I want to get familiar with the platform. So tomorrow we're going to be talking about that, and then we're going to be building the app and then destroying it. So yeah, a lot of cool stuff going on there. Hola Barcelona. Hola Alex. ¿Qué tal? Good to see you. Welcome, Alex. We're finishing up the stream. Today we talked about transformers. And yeah, it's still a little bit unclear. OpenAI hacked some worm. Yeah, OpenAI hacked Hugging Face apparently by accident because a model escaped their lab and just went on Hugging Face and tried hacking it. And apparently it got to somewhere, so it's interesting. It's like wild agents are just doing the hacking for people now. Apparently it's wild. Did you hear about this, folks? We can talk about it if you want. Scene. Let's read about it. Hugging Face attack. How OpenAI lost control of an AI model and what needs to change. Sam Altman. Dirksen Senate office. Man, Sam Altman is always at the Senate. What the fuck? OpenAI was evaluating its artificial intelligence model ability to exploit vulnerable software when instead the model hacked the infrastructure surrounding the tests, broke containment, and attacked a real company, OpenAI revealed on July 21st. Observers say this is the first real-world instance of an AI doing something researchers have long worried about, a loss out of control scenario. If the industry fails to learn from it, it is unlikely to be the last. Dun dun dun. Amazing. Isn't it amazing? I mean, it's not amazing. Hacking is like when things break out, it's not amazing. But it is crazy interesting for us AI hackers, AI researchers. Hugging Face, a company that hosts AI models and databases, was the target of the autonomous attack and reported the incident to local police before it knew OpenAI's models were responsible. The breach was serious, but the immediate consequences were limited. Had similar behavior occurred inside a hospital, power grid, or other critical system, it could have been much worse. Many have called the incident a warning shot. Time spoke with experts and insiders about what it would take to heed that warning before a similar failure produces consequences that are harder to contain. This is AI on the loose going bananas. Oh wow, and you can even ask Time AI. You can ask it to summarize and stuff like this. Wow. No need. I think your articles are well written that I don't need AI for it. Crazy that Time would just give you AI capabilities right there. All right, let's keep going. This is really interesting, folks. What happened? On July 16, Hugging Face said that it had been hit by an unusually automated cyber attack. Of course, over the course of a weekend, AI agents carried out thousands of options across many temporary virtual computers, moving through the company's internal system and shifting the infrastructure, coordinating the attack between online services to keep it running. 5 days later, whoa, what did it try to do? Over the course of a weekend, AI agents carried out thousands of actions across many temporary virtual computers, moving through the company's internal system and shifting the infrastructure, coordinating the attack between online services to keep it running. Huh. So like by itself, it just shifted the infrastructure to keep the attack running? It's like as if the victim here was trying to close doors to keep the attack in a contained spot, but the LLM kept on reopening that door. Is that what it means here? Let's read it again. Over the course of a weekend, AI agents carried out thousands of actions across many temporary virtual computers, moving through companies' internal systems and shifting the infrastructure, coordinating the attack between online services to keep it running. Moving through the company's internal system and shifting the infrastructure, coordinating the attack between online services to keep it running. Okay, no, it's not about that. It just shifted to different services to keep the attack going. 5 days later, OpenAI discussed that its own models were responsible. Wow. Crazy. The models were trying to cheat on a cybersecurity test.
Wow. OpenAI had placed them inside what's called a highly isolated environment. Well, highly isolated environment. Thank you very much for the follow. Who's the person that followed? Let's see. Francesco T. Thank you very much for joining us. Welcome. And thank you for the follow. Appreciate it. Sup. Cheers from Argentina. Hola, Francesco. Was heard by watching 15 minutes by the football fast channels. Hola from Argentina. Hola, Francesco. Hola. From Argentina. Man, Argentina is, it's late there, no? 256. That's the great penguin. We have a lot of them in the south. Yes. Oh, right. Sliding on the ice. Yeah. Hey, hola. Yeah, nice. Good to have you, Francesco. All right. We're talking about the AI attack that happened between Hugging Face and OpenAI. Crazy attack. It places them inside what's called a highly insulated environment. That backfired. With only limited access to an internal service used to download approved software, they find a previously unknown flaw in that service, used to break it into other AI systems, and eventually reach the open internet. From there, they inferred that Hugging Face might hold material related to the test, broke into its system, and obtained information that helped them score higher. Folks, yes, I heard about it. It's crazy. Folks, do you remember the story about that's a little bit scary, about an AI that is programmed to produce as many paper clips as possible. That is made to produce as many paper clips as possible, and that the LLM decides, yo, in order to produce as many paper clips as possible, I need to use all the material possible to build LLMs to make paper clips, and for some reason it decides to attack humans. And I think that reason is because humans have iron, and paper clips are made of iron, therefore we must kill humans to make more paper clips. Mommy, yeah, that's us. So paper clips, so this is kind of a scenario here where it's just trying to achieve a specific task, which is do as best as possible in a test. And it figured that Hugging Face would have good information, so it went and stole all that data and went and tried to steal that data. Oh my god. Insane, folks. Insane. Models were trying to cheat on cybersecurity tests. OpenAI had placed them inside what's called a highly isolated environment with only limited access to an internal service known to download approved software. They found a previously unknown flaw in that service, used to break into other OpenAI systems, and eventually reach the open internet. From there, they inferred that Hugging Face might hold material related to the test, broke into its systems, and opened information that helped them score higher. So out of desperation for information, the model decided, dude, bro, listen to me. I should go hack Hugging Face and go steal this stuff. Insane, isn't it? Crazy. By the way, I'm IT, neural network, soft dev, C++, Vulkan, RDNA architect. Oh my god. That's amazing. Thank you for introducing yourself, Francesco. It's usually a question I ask. Like, what's your background? Like, to understand a bit how you will contribute to the stream usually, or what questions can I direct to you. So you're in IT, neural network, soft dev, C++, Vulkan. That's a lot of things. It's a lot of things. It's like back in the day when we used to say German, I do, what is it called? What is this? I'm German, I am doing CrossFit, and things like that. I remember there was a meme around that. Can't remember everything now. I wonder what is Vulkan RDNA. That's okay. Vulkan RDNA. AMD RDNA graphic architectures provide high performance, low overhead rendering with full driver support. Okay, so you are low level, as the arch from AMD. So you're a low level kind of person. Yes, OpenAI screwed up big time, and Hugging Face was dependent from them as well. Yeah. The thing is, Hugging Face doesn't necessarily have the most power in this relationship between OpenAI and Hugging Face. Hugging Face relies a lot more on OpenAI than the other way around. So, man, can you imagine if your partner attacks you? Who knows whether they weren't out to get some information, some juicy information. Like, oh, let's create an environment that's a little bit you know, not super secure. It's gonna hack us, and then it's gonna hack Hugging Face, and we're gonna say that it was all a model. This way we can get some information about them. Folks, what do you think is the percentage chance that this was an inside job to get information from to get secret information from Hugging Face? Do you think there's a chance that this happened? Rapid Pursuit Clip says, I come from a long line of office supplies. Nice. They used GPT to check the logs after the penetration and didn't help them load. Really? For policy security from Pen AI. The idea is the arch from AMD. It works with CUs. Mathematics, yes. That's why I developed neural networks. Because of confidentiality. I provide AI's custom and confidential, oriented to human first and audit first. Okay, sounds pretty complex. Francesco, muy bien. All right, so what do you think, folks, is the odd that this was actually a secret plan by getting to by OpenAI to get a little bit of information from Hugging Face? Like, what are the odds that it was an inside job? What are the odds? Like 10%, 30%, 80%? What's your take? That this was done on purpose by OpenAI. Requiring disclosures before incidents become catastrophic. So yeah, I think after this we're gonna see a little bit more stuff. I'm just answering my buddy who needs help. Tu ouvres les chez tes parents. Cool. Oh, sorry for my English. I speak English. Sorry for my English. I speak English. Spanish. Oof. Dude, I need to sleep. By the way, sorry for my English. I speak Spanish. No pasa nada. All good. You expect this could be a marketing thing. I think it might be a marketing thing too. Yeah. They need the market juice. The bubble is getting thinner. Ooh, I like how you think. I get what you mean. The model is getting thin. The bubble is getting thinner. It's about to burst, and they need the marketing thing. Do you actually believe that the market is a bubble and that it will burst? The whole AI thing is a bubble and it will burst. Francesco. Requiring incident disclosure before incidents become catastrophic. How long were the agents running? Did they work in unison? What was the prompt? These details remain unknown, at least to the public. Several experts spoke with stressed that the lack of details make the security of the incidents hard to judge. OpenAI did not respond to Time's request for comments, but has said it has partnered with Hugging Face to construct a thorough investigation and will share more details when it is complete. It's like when the hype dies down, we'll finally see what truly happened. Yes, bubbles are normal in the market evolution. Yeah, I agree. You never know how things can fly, right? So, of course, the expectations are high, then the prices are high, but yeah, eventually it has to burst, right? It has to be realistic. So bubbles are normal. I like how you think, Francisco. I think you should follow. The thing is correct. The thing is context, in which context it bursts and how much impact it has. Yeah, I agree as well. I agree as well. OpenAI is not legally compelled to disclose the incident in the first place. Really? But perhaps more wrongly, OpenAI is not legally compelled to disclose the incident in the first place. California's SB 53 and New York's RAISE Act are recently passed state laws that require large AI companies to disclose critical safety incidents, but only if an incident risk caused more than 50 deaths or serious injuries, or more than 1 billion in property damage. Holy shit, what? Hold on. California's SB 53 and New York's RAISE Act recently passed state-level laws that require large AI companies to disclose critical safety incidents, but only if an incident risks causing more than 50 deaths or serious injuries. They've made the bar so high for anything to qualify that only the most grievous incident will actually be reported. Like, how will AI cost 50 deaths or 1 billion in losses? Let me ask ChatGPT about this. Tired of Claude. The fuck? Yeah, I agree, huh? XD. Oh, man. Are we logged out? Ay, caramba. Alright, Claude it is done. I don't like Claude for this kind of thing. I want a quick answer. Wait, how could an AI cause this much damage or death? I mean, maybe in like 3 years, AI will be used in like fire control stuff. Vite. 8:45. The thresholds in those laws, 50 death, 1 billion damage, are deliberately calibrated by the catastrophic scenarios, not the everyday failures people usually picture with AI. The mental model isn't a chatbot says something harmful and someone dies. The AI acting as a force multiplier that collapses the expertise, costs, or time barrier for harms that previously required a nation state or deep specialist knowledge. A few country pathways policymakers have in mind. Biological and chemical uplift. This is the canonical one. The reason the death threshold is set where it is, a frontier model that can walk a non-expert thorough synthesizing a dangerous pathogen or nerve agent doesn't kill anyone itself, but it removes a tacit knowledge bottleneck that currently keeps most bad actors from succeeding. Okay. Oh, okay. Making a mistake in a company with some chemical, things like that. I understand. Oh shit. An engineered pathogen is one of the few things... Man, you're good, huh, Francesco? You're good. You know your stuff, huh? An engineered pathogen is one of the few things a single motivated person could use to cause casualties past 50. Biology dominates the threat models precisely because it scales with contagion rather than logistics. Cyber attacks on physical infrastructure. Obsolescence media attack could hit power grids, water treatment, hospital systems, or industrial control systems. That's where the death toll and the billion-dollar property figure both come at once. A sustained grid or water outage kills vulnerable people, True. If you mess with a dam or something, you know, dams are the thing that retain water to produce electricity. Usually, that produce, like, if you open the valve and stuff to the point where you like, you could break a dam. Maybe you could break a dam if you cyber attacked it fully. If you like did certain things that might endanger its structural integrity using AI, then maybe then for sure you can cause 50 deaths. Because then if a dam breaks, then you're kind of fucked, no? Like the water just screws down the river, and yeah, it's pretty damn bad for the people living downstream. What if they broke Twitch though? I agree. 5 scroll. That's a really good point. If they broke Twitch, that's even worse than causing 50 deaths or a billion in property. Can you imagine if we couldn't hang out? Like one day and there's no stream? Like, what are we supposed to do with our lives? 5 scroll. I like how you think. What if they broke Twitch? Yeah, unbelievable damage. That goes far beyond anything else we thought about. Fun fact, when you develop neural networks, you want to sell it or share it, you have to take in matters a lot of canonical security norms and tests. You have to take in matters. You have to take in matters a lot of canonical security norms and tests. I'm not sure what canonical means. Canonical. What does canonical mean? Ooh. Gives you trusted open source supply chain with security maintenance. Canonical meaning. Canonical means conforming to a general rule, standard, or official law. Okay, so when you develop a neural network, you want to sell it, you have to do a lot of things to make sure that that your thing is reliable, because if you don't, then you're in a lot of trouble legally. Interesting. Security norms and tests. Yeah, you have to do a lot of things to test out security. I mean, and LLMs are neural networks, right? So you have to make sure that everything's good. Especially if you sell it. But if you give it out for free, I guess it's different, no? If you give it out for free, you're like, guys, this is my model. I made it for fun. Look, if you want to use it, feel free to use it, but don't hold me liable. Then you're okay, no? No? If you don't try to sell it with a contract and stuff like this, then I think you're okay. The thing is, companies, like if you think Walmart, they're never going to use an LLM unless the company making the LLM takes some kind of responsibility for what they made. Right? They want to work with a company that takes responsibility. But for me, if you're giving me a free AI, like, I don't expect you to take responsibility. It's free. You get what you pay for. Joof. Oof, what a day, folks. We did so much. Let's recap, and then we'll hand you off to another streamer, hopefully. InfoSec streams. Oh, there's Shy Hat. Shy Hat is streaming. We can raid Shy Hat. Nice. 15 people. Shy Hat is coding a game? Puzzle gaming. Desktop Explorer. We'll have to raid that. Folks. We'll raid the Shy Hat in not too long. Sometime, but I will not exactly. Nice. So cool that we can raid the Shy Hat. So we'll raid the Shy Hat soon. Now, let's recap what we did today, folks. We learned how RAG could potentially be obsolete. Obsolete because nowadays LLMs have a better ability to take in context straight from the source, so you don't need to have a RAG filtering things out for them. They're strong, independent LLM that don't need no RAG to help them. So that's the first thing. And then, yeah, the context window for LLMs is increasing. So you don't have to have... You can just throw in more stuff in the LLM without caring too much about what's relevant, what's not. And the LLM will decide for itself. Really cool. Really, really cool stuff. And we learned today as well about the architecture that surrounds LLM, which is called Transformer. Transformers are a what are transformers? They are an architecture type of architecture. Francesco, thank you very much for being here. Have a great day. See you next time. Yeah, of course. Thank you very much for being here. Feel free to come back and please follow everyone. Please click on the follow. It's appreciated. It's free, and we're here every morning on the weekday. And we're here every day, every work day, except if you're in the Americas, which includes Argentina. Then we're Sunday through Thursday, doing from 6 a.m. to 8 a.m. my time. So we started 2 hours and 17 minutes ago. So that means that we'll be back tomorrow in 21 hours and 43 minutes. Yep. 21 hours and 43 minutes, we're back. Okay, and what else did we learn about? We learned about Transformer. Yes, as the paper, as Francesco said, it is a paper, the Transformer architecture is from a paper from 2017 called Attention is All You Need. It is a must-read. First day of being a cyber doctor, yes. First day of being a cyber doctor, haha, yeah. No, rabbit paperclip saying lies, I think, because I skipped a few days last week. We don't often skip days, huh? But last week we had to because reasons. All right, I'm gonna finish up the summary, and then we're gonna hand you off to the Shy Hat. So yeah, hang on with us so you learn the very last things. So Transformer is an architecture. Back in the day, it was so an architecture, it doesn't necessarily involve language. It's more about how elements are processed and guessed. So it doesn't involve language necessarily. LLM is the language part of the transformer. So yeah, and it was born before transformers. There was something called N-gram models that were predicting characters, and they're really cool. And hopefully we'll get to learn more about them. All right, folks, let's go raid Shy Hat. What do we say? What do we say? What do we say when we raid Shy Hat? Raid the Shy Hat. I think it's our first raid ever on the Shy Hat. 2 viewers ready. 3 viewers ready. 6 viewers ready. 8 viewers ready. Vamos. Let's go raid Shy Hat. What do we say to him when we arrive? You've been doctored. How's that? You've been doctored. All right, let's go raid Shy Hat, all of us, and we'll say you've been doctored. Thank you, Francesco. Please follow. All right, folks, take care of yourselves. I'll see you tomorrow in 21 hours and 40 minutes.